Swayam Prabha. Digital India. Educated India.
Hello, welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. So we have in our background our usual motivating image, which is essentially a rover on Mars. And these sort of vehicles are driven autonomously because it's not usually possible to have sort of humans controlling the equipment at all times uh, on these extraterrestrial locations. So we want to be able to, of course, analyze and learn to develop algorithms that are going to drive systems such as these, right? So until last time, what we were doing was essentially discussing the notion of positive definiteness, right? So this is what we were doing until last time. We were talking about positive definite functions, right? So this was one of the building blocks in the Lyapunov theorems, right? So we talked about what is a positive definite functions, and after that we sort of wanted to look at a few easier tests for positive definiteness, right? So we saw the definition, but then it's not always easy to apply the definition, and so we wanted to look at some additional tests, and we looked at these easier sort of tests that can be applied, and we sort of also saw the connection between positive definite matrices and positive definite functions through an example, right? So through this example, right? And of course we saw another example for positive definite function also, right? So we sort of go ahead in this vein of discussion, and the next sort of function is a radially unbounded function. So let's sort of start our lecture 4.2 here, right? So we are starting to talk about radially unbounded functions. So radially unbounded functions are sort of the next level of functions. As you can see, you have scalar valued continuous function again. Of course, this should be R. I guess we use R here too. Let me see. Yeah, we were using R here, so I guess we can continue to use R here, although R plus would suffice in all these cases. Okay, we don't necessarily have to use R itself, but R plus is good enough, right? So non-negative reals for time is usually what we have, right? So we are of course looking at a function of time and a space variable which maps to real numbers. This has always been the setup for these functions that we denote as v, which are essentially going to be our Lyapunov functions subsequently, right? So what do we require? We require that the function be 0 at 0, right? So at 0 value of state, the function has to take the 0 value. So this was the same condition for positive definiteness also. The big difference happens here. We want the existence of a class kr function, which this function vtx dominates. Okay, so in the case of positive definiteness, this was a class k function. Right? So what's the difference between a class k and a class kr function? We have in fact seen several examples, right? So if you have a class K function, it can be something like, I mean, you're allowed to have something like this, function which sort of grows, but stays bounded below this. So it's always increasing but stays bounded below this. On the other hand, class K infinity function has to be something like this. I mean, it keeps growing and goes to infinity. Yeah, as t goes to infinity. So here, of course, here you have the x and you have sort of phi x here, right? And since, of course, these functions are take as arguments non-negative reals, obviously you use a norm. Right? This is what we have been doing, right? So if just to compare again with the definition of positive definiteness, it was the same sort of expression, phi norm of x. The only difference being that here it was a class K function, right? And now in the case of radial unboundedness, we require V to dominate a class KR function. So this naturally sort of implies that this domination has to be for all time, right? However, notice that just like before, we do not require, if you think about it, we don't require the V to be a continuously increasing function, like a class KR function is of course a always increasing function, always strictly increasing function, right? But all we want for V is to dominate this class K function, right? And notice that again, unlike the definition for positive definiteness, here this lower bounding has to happen for all x in Rn, right? In case of positive definiteness, it was sufficient if it happened for x in some ball. Therefore, we had this nice picture, right, where beyond this ball, the V was allowed to drop below the class K function. Okay, so essentially the idea is that it can give us local stability properties, right? So the idea of positive definiteness being defined in this manner is that it helps us conclude local stability properties. On the other hand, radial unbounded is typically used to conclude global stability properties, right? And so we require this function V to dominate this class KR function, right, which is this guy in this particular case here, for all time and for all values of the state. Okay, so this is much more stricter condition, as you can imagine. However, this still does not require that my function V be increasing or anything. It can be oscillating like this as long as it is bounded above just a second, as long as it is bounded above your class KR function, you are fine. Okay, so this is sort of an example, right? This picture sort of gives you an example. The only thing is there's no crossing happening anymore, right? It always has to lie above this class KR function curve, right? And in such cases, V is said to be radially unbounded. And just as we already stated before, radial unboundedness is related to notions of global stability. Okay, just like positive definiteness is connected to local stability, radial unboundedness is connected to global stability. Okay, what would be examples? Very simple examples. I mean, say I have x in R2 and denoted as x1 comma x2. So Vx1 x2 equals to x1 square plus x2 square by 2 is in fact a radially unbounded function. Yeah, why is it radially unbounded? Because if you look at this function itself, this in itself is a class KR function, right? This in itself is a class KR function. Why? Because it's 0 at 0, right? If you plug 0 value of the state, that is x1 and x2 are both 0, which is what it means for x to be 0, right? I get a 0 here. And it is strictly increasing and going to infinity as any x goes to infinity. So in any direction, if you go to infinity, this is going to go to infinity. All right. So therefore, this is itself a class KR function. Therefore, V is in fact a radial unbounded function also. Every class KR function will also be a radially unbounded function. Of course, I can have slightly more involved examples, like I can take something like V with T also, x1 x2 as T by 2 x1 square plus x2 square, and here of course T is greater than or equal to 0, right? So here of course this is this is greater than equal to half x1 square plus let me be careful here. Let me say this is not T, but this is T plus 1. So this is greater than or equal to half x1 squared plus x2 squared, because T plus 1 is greater than or equal to 1. So therefore this is greater than or equal to half x1 squared plus x2 squared. So implies V is again radially unbounded. Okay. So we can also have, let's see, let me try to think. We can also have some kind of oscillating examples like the one that we showed in the picture, and that can be constructed say by again introducing a time variable as 1 plus say sine squared t divided by 2 x1 squared plus x2 squared, right? So this is again greater than or equal to half x1 squared plus x2 squared, because sine squared t, this is of course greater than or equal to 0. So this is fine, and this is radially unbounded. But what this term is going to do, right? What this term is expected to do is to sort of make things oscillate around a bit. Yeah, make things oscillate around a bit. So this term is going to contribute to some oscillation, but in time, right? Here, if you notice, the oscillation was with the state itself, right? That can also be constructed, right? I'm not doing it here, right? But that can also be constructed. Okay, so I would really urge you to give it a thought as to try to construct such a Vx. Okay, try to construct such a Vx, right, where it's x and it's oscillating with respect to x itself, but it's still dominating a class K function, right? Still dominating a class K function. It's not too difficult, honestly speaking. Yeah, it's not too difficult. I mean, you can think of, I mean, simple ideas are like, I can add an oscillatory signal to x squared. Yeah, something simple like that. Yeah, as long as I do that, I'm also still okay. All right. Okay, so these are all examples of radial unbounded functions. Again, relatively simple examples. Okay, but again, when things become more complicated, we do require easier conditions. Just like before, just like the case of positive definiteness, we do require easier conditions to verify radial unboundedness also. Okay, so what is it? So again, if I think of the case when V is not a function of state, and remember that V is not an explicit function of time, and remember, whenever V is only a function of state, we have been using Wx as the notation, right? Do not get confused at all. I'm using V and W almost interchangeably. It's just the purpose of the function is what is important than the notation of the function itself. So whenever V does not depend on time explicitly, I am denoting it with Wx. Okay, so whenever it's just a function of the state, right? Then I have three requirements. Right? First is that W0 has to be 0. Wx has to be strictly positive for all non-zero states. Again, I'll come to the difference between the positive definiteness case soon. And finally, Wx has to go to infinity as the state goes to infinity. Okay, so this is important. It has to go to infinity in any possible direction. It has to go to infinity in any possible direction. So what is the difference? First of all, let's try to see what's the difference from the easier condition for positive definiteness. Okay, so let's keep this in mind. Yeah, and remember that this third condition did not even exist for positive definiteness. There was no requirement for the function to go to infinity at all. So obviously this third condition is completely distinct, right? So we are not even going to discuss it. Let's look at the first two conditions only. Yeah. If you look at the first two conditions, you require the same first condition, that the function itself be 0 when the state is 0. There's no difference there. This is pretty much uniform along all definitions concerning Lyapunov functions. Yeah, that the function needs to be 0 at 0. Why? Because 0 is where we are interested to go to, right? So think of the Lyapunov functions or these V functions as some kind of energy functions, right? And we want the system to settle at the origin, that is x equal to 0. Therefore, we want the energy, the so-called energy or this notional energy function, to also be 0 or minimum value at 0 at the origin, right? It doesn't make sense otherwise, right? Yeah. If it's not at the minimum value when it's at the origin, then it could possibly go lower, right? And therefore, we will move from the origin. Right? Doesn't make sense since we want to stay at the origin, right? So all these functions invariably require that they be 0 when the state is 0. So this condition is identical, no difference. The second condition is where there is a small change. It is positive for all x, but in a ball, removing the origin. It only has to hold true in a ball. Okay, of course, removing the origin. But here we need it to happen for all Rn. This is also because how radial unboundedness is defined, right? That this domination has to happen for all Rn. Right? Everything has to happen for all Rn because we are talking global notions here. Okay, so this is the difference. So the first two conditions, if I may, I would like to call it some kind of global positive definiteness. It is still positive definiteness. The only thing is we are requiring something more stringent, that this positive definiteness hold for every value of state other than the origin and not just in a ball around the origin. Okay, so this is a little bit more stringent. And beyond that, we require that the function goes to infinity as the state goes to infinity. So what we want to do to look at this in a sort of easier condition thing is to look at a lot of counter examples, right? So, and that really helps us to understand what is not a radially unbounded function, right? So I'm going to label this counter examples, okay? And one, v, no, apologize. V x1 x2 is equal to half x1 plus x2 squared. Okay, so the question is this positive definite? Is this radially unbounded? Okay, so we have to answer all these questions. So the first thing that you need to notice is that along x2 equals minus x1. What is this? If I look at the state space, I'm going to draw the state space, right? This is x1, this is x2. I don't know why that's happening. Right? This is x1, this is x2. And what is x2 is minus x1? I believe it is something like a line which looks like this. This is this. X2 is minus x1 is this line, right? So this is x2 equal to minus x1. So what happens along this line? So I cannot, of course, draw it because it's I'll have to do it in 3 dimensions. V takes 0 value. Okay, so V equal to 0 all along this line. Okay, and that is a problem, right? That is a problem. Right? Why? Because since V not greater than 0 for all x1, x2 not equal to 0. In fact, there is a line which can go all the way from 0 to infinity and minus infinity, where V is in fact not positive at all. It's in fact exactly 0. Therefore, V is not even satisfying the first 2 conditions, right? So this is you can very safely say that not positive definite even. Yeah, so forget radial unboundedness. This function is not even positive definite. Okay, so definitely doesn't work. Next counter example. So I'm sorry, I should have used W, but okay, that's fine. I've used V. But again, let's remember we are using V and W interchangeably, and it's the purpose that it serves is what is valuable to us and not the notation. Okay, so let's not get too confused or too hung up with the notation. Okay, all right. So let's look at V. Well, W. Now I will use W. Right. X1, X2 is equal to half x1 square plus 1/4 x1 4. Okay, is this positive definite? Does it satisfy? So of course w0 is 0. Great. Okay, but what happens? Let's see. W of all 0 comma alpha is also 0, because notice there is no x2 here, only one state appears. So whenever you have a function which has only one state, what happens? I can just say w0 alpha is equal to 0, which implies w not positive definite. And if it's not positive definite, implies w not radially unbounded. Yeah, because I need minimum positive definiteness to even go to radial unboundedness. Okay, so no, answer is no again. Okay, so if you have any function which has only some of the states appearing and not all of the states, it is immediately not a positive definite function and therefore not radially unbounded. Okay, so you don't even have to do any calculation. Okay, because you can always make an argument like I made here. Okay, great. Let's look at a slightly better example. W x1 x2. Well, let me use something better. We have already seen this example. Wx, yeah, where x can be in Rn. Yeah. So what about this? Does this satisfy the first 2 conditions? One is 0 at 0? Yes. W0 is in fact 0. Yeah. What else? Wx is in fact positive for all x not equal to 0. It's obvious because if x is not 0, norm x is positive. We already made this argument. So this immediately implies norm x is positive, and I'm done. Right? If norm x is positive, right, then this is positive. This is again some positive denominator, so it doesn't matter. So wx is positive. So of course it satisfies the first two conditions. Great. Yeah, excellent. We are happy. At least we have something that's positive definite, right? Which we already proved did prove in the previous lecture. Okay, so this is not a different example. What about radial unboundedness? That is, what about the third condition? Does it go to infinity as x goes to infinity? As you can see, the answer is no, right? Why? This is where I had written a sort of expression for w last time. This is where it will come to be of use to us, right? So wx can be written as 1 minus 1 over 1 plus norm x squared. Okay, so as x goes to infinity, wx goes to 1, right? Because as x goes to infinity, this goes to infinity, so this whole thing goes to 0, and so all I'm left with is 1. So this is one of those functions which is a nice positive definite function. So from here I of course had this is positive definite, but because of this implies w not radially unbounded. RUB is the notation for radial unboundedness. Okay, so it's a positive definite function, but it is not radially unbounded because it doesn't go to infinity as the state goes to infinity. Okay, so this is rather critical. Okay, rather critical distinction. So function like this cannot be used to prove global stability. Okay, all right, it will not help us prove global stability properties. Okay, that we'll see later on, of course. But yeah, so this is not a radially unbounded function. All right, excellent. So all right, so these are sort of the the easier condition corresponding to radial unboundedness. The second condition is when we have a function of both state and time, right? Both time and state appear exactly, exact parallel to what we did for positive definiteness. We had one condition for when we had a function of the state only, and another condition when we had a function of both the state and the time explicitly. All right. In such cases, we just use the previous easier condition, right? We just, again, just like positive definiteness, we just use the previous condition. What do we say? It still has to be 0 for 0 state values and all time. Okay. But we say t in r plus here, of course. So fine, that's non-negative time. I mean, anyway, to be honest, just to prevent ambiguity, it's better to say it is r plus here. Yeah, for all definitions of v, time in r plus is quite okay. Okay, because we never deal with non-negative with negative time. Okay, so we have vt0 equal to 0 is obviously a standard requirement, but the next requirement is simply using our previous positive radial unboundedness definition, is that this vtx has to dominate a radially unbounded function of the state only. Okay, vtx has to dominate wx, which is a radially unbounded function of the state only, where wx is radially unbounded. Okay, so wx is a radially unbounded function of the state only. Okay, in this case, of course, constructing examples are really easy. I can simply take a v v tx as again something like t plus 1 by 2 and norm x squared, and we know that this is greater than equal to half norm x squared, which is of course radially unbounded. So this implies that this is radially unbounded. Okay, so it's not very difficult to construct such radial unbounded examples of both state and time. All right, great. So what did we look at today? We essentially did the exact same thing that we did for positive definiteness for the case of radial unboundedness, which are functions which in addition to positive definiteness globally also go to infinity as the state goes to infinity. We looked at some easier conditions to verify this radial unboundedness also, right? So again, of course, we will continue with the next set of functions uh, in the upcoming lectures. So that's it. Thank you for joining me.